Our final section in chapter 1 talks about the intersection of straight lines. So section 1.4 part 1, let's talk about how we find the intersection of straight lines. So again, what we're talking about are two lines that cross, and we need to find where they cross. So there are several different methods. There are two methods you should already be familiar with that we'll do in this section. So example 1a, we have two equations, y equals 3x plus 4, and y equals a negative 2x plus 14. Both of these are linear equations or linear functions. We're going to use the substitution method for this example, mainly because they're both set up as y equal to and y equal to. So I'm simply going to substitute the 3x plus 4 in place of this y. And that would give me a brand new equation that has just a single variable in it. So again, we're replacing this y with what this y is equal to, which is 3x plus 4. So now we have a linear equation with just x's as the variable. 3x plus 4 equals a negative 2x plus 14. We're going to solve that. So we'll add 2x to both sides. That's going to give me 5x plus 4 equals 14, and then we'll move the 4. So 5x is equal to 10. Dividing out the 5 is going to give you an x value of 2. So we're more than halfway done, but we have half our answers. Now don't forget we're looking for a point in space, and that point in space needs both an x and a y coordinate. Well, we found the x, we need to find the y coordinate. To find the y coordinate, we're simply going to plug this x back into either equation. I'll use the top equation just because it doesn't have that negative on the x term. So y equals 3x plus 4, but we now know that x is 2. So we're going to plug in 2 plus 4. That's 6 plus 4, which gives us 10. So we end up with a solution of 2 for our x and 10 for our y. And you should be able to plug this into either equation and verify it. So if we plug in the 2 for this x in the second equation, we're going to get a negative 4 plus 14 gives us the 10, which is what we said it was equal to. That's the substitution method. Another method that you may already be familiar with, or you should, is the elimination method, sometimes referred to as the addition method. This method relies on adding the two equations together and eliminating one of the variables. This is example B, 1b. And our equation there is 2x plus 4y equals 11, and then negative 5x plus 3y is equal to 5. So 2x plus 4y equals 11, negative 5x plus 3y equals 5. You'll notice that on this set of equations, we don't have a y equal to or a y equal to, so the substitution is not as easy. If I try and isolate y, it's going to get pretty ugly on us. Instead, we're going to multiply and get rid of one of the variables. I'm going to pick on the x's. The reason is one of these is a positive quantity, the other one is a negative quantity. We're going to multiply the top equation by a 5. We're going to multiply the bottom equation by 2, creating a common coefficient of 10, one positive, one negative, and they'll cancel out. So I'm going to write that next to it. So that would give me 10x plus 5 times 4 gives me 20y equals the 5 times the 11, which is 55. On the bottom equation, 2 times the negative 5, x is going to give us negative 10x. 2 times the 3y gives me 6y. And finally, 2 times that 5 is going to give me a 10. Now we'll just add the equations and eliminate the x's. So now we have 26y is equal to 65. Then we'll come in and divide out the 26. Double checking my arithmetic just to make sure I'm on the right track. So we want to try and divide these, see if we can divide them out. I think they'll both divide by 13. So 65 divided by 13 is 5, and 26 divided by 13 is 2. I was reducing it in my brain and not coming up with what I wanted to. So I get y equal to 5/2. It's a fraction, which is okay. We can get fractional answers. But now I need to find the x value. So we're going to take that y and plug it into either equation. Because it's the y, I want to plug it into something that's going to work easier for us. If I multiply 3 by that, the answer or result is uglier than if I multiply 4 by that. So we're going to take our 2x plus 4 times that 5/2 is equal to 11. Well, 4 times 5 is 20 divided by 2 is 10 equals 11. And move your 10. We'll get 2x equals -1, and then x is equal to sorry, positive 1, x is equal to a positive 1/2. So we get a solution of 1/2 with our x value and 5/2 for our y value. Again, you can plug both the x and the y into either equation and verify that it works as a solution. So those are two different methods to find where two lines cross. So the rest of the section is devoted to applications where lines are crossing. So example 2 is a break-even analysis. So the problem reads, a division of Carter Enterprises produces personal income tax diaries. Each diary sells for $8. The monthly fixed costs incurred by the division are $25,000, and the variable cost of producing each diary is $3. This should look slightly familiar from the last time we talked. So the very first thing they want us to do is to write the cost function and the revenue function. So if you remember from the previous section, the cost function is the fixed costs plus the variable costs. And for this problem, the fixed costs were $25,000. And the variable cost of producing each diary is $3. So that would be 3x. You can write that as 3x plus 25,000. It does not matter in what order you're writing it. The revenue function is how much you make from selling each of the diaries, which is 8x. So there's the cost function, there's the revenue function. They want us to sketch the graphs of the cost and revenue functions and graphically mark the break-even point. So let's graph them first and then talk about what the break-even point is. So to graph them, what I'm going to do is just plot a couple of points, not a lot of points. The x-axis here is the number of units that we're producing and selling. The vertical axis is the cost or dollar amount. So we know we're going to need 25,000 to start with. So I'm going to count by literally 25,000s and see what's happened. So on this axis, I'm going to do 25,000, and then I'll do 50,000, and so forth. Okay, on this axis, the number of units, I'm going to put them in terms of 1,000. Because if I put in 1 unit, I'm not going to vary very much off this 25. But if I put in 1,000 units, I should vary quite a bit. So let's just go figure out what 5 units is going to be. So I'm literally plotting points here. If I plug in 5,000 units here, I'm going to get $40,000. So 5,000, 40,000 would be about here. If I produce, or I'm sorry, if I sell no units, then this would give me 0. So my revenue function looks something like this. So there's R of X. I'll do the same thing for the cost function. I know its y-intercept is 25,000. If I plug in 5,000 units, that would be 15,000 and 25,000. Look at that, I hit it on the nose, is 40,000. So this one's going to come in and do this. And there's the cost function. This point right here, which I got just by giggles and grins, as they call it. I was lucky, I just got it. This point right here where the revenue and the cost is called the break-even point. Again, that's where the revenue and the cost are equal. And it's an intersection of 2 lines. And they're asking me to go find that. So let's go, oh no, it says graphically mark the break-even point. And then part C, it says algebraically, part B is the graph, find the break-even point. So we need to find where those 2 lines are crossing. We're going to use the substitution method. What we're recognizing is that this is equal to y and this is equal to y. So we're going to set the 8x equal to the 3x plus 25,000. In case that is not making sense to you, the break-even point occurs when the revenue function is equal to the cost function. So when the 2 are equal to each other, you get the break-even point. We just need to solve this. So moving the 3x is going to be 5x equals 25,000, and x is equal to 5,000, which we already knew by accident. That's that 5 that came in over there. To find the y value, we just plug it back in. So I'm going to plug it into the revenue because that's a bigger one. R at 5,000 would be 8 times 5,000, which is 40,000. So what we're maintaining is that if we make 5,000 of these diaries, so 5,000 of the units, will be spending and gaining $40,000. So that's our break-even point, which we'd also found over there graphically, but algebraically it makes a lot more sense. And then it says, let's sketch for part D the profit function. Well, we need to find the profit function. So from our work the other day, we know that the profit function is the revenue minus the cost. So part D, the profit function P of X is the revenue minus the cost. So that would be 8x minus the quantity 3x plus 25,000. So that's going to give me an 5x minus, because we're going to distribute the negative, the 25,000. So if I want to sketch it, I'm down here at a negative 25,000. And again, I can plug in 5 again, or yeah, the 5,000. If I plug in 5,000 for x, I'm going to get 0, which makes sense because in terms of money, the break-even point occurs where you go from a profit that's a loss to an actual profit that's a gain. So the break-even point happens when all of this is going on. Part E is trying to make sure that makes sense to you because it's asking at what point does the graph of the profit function cross the x-axis. So the profit function crosses the x-axis at an x value corresponding to the break-even point. So when you're solving systems of equations, you're asking yourself, when am I ever going to need this? Well, you need it to find the break-even point and to figure out when the profit goes from a loss to a gain.